Welcome to Exponential Growth and Decay. Let's get started. Alright, so we have a couple of essential questions. This is a long video. What b value do you need to represent exponential growth? What about the decay? The next one is, what are examples of keywords that we would want to identify to tell us if a word problem is referring to exponential growth or decay? So you'll read a word problem, and there'll be some specific words that you can circle or highlight that will let you know right away that we're either dealing with a growth or a decay. What are those? So let's define exponential growth and decay. So any quantity that grows by a fixed percent at regular intervals is said to possess exponential growth. Whereas any quantity that decays by a fixed percent at regular intervals has exponential decay. So these are our definitions: a quantity that decays or grows by a fixed percent at regular intervals. So this is an exponential equation in this form with y equals a times b to the x. So b is the base, and then x we have as our exponent, and then this a value is being multiplied by the base. So we have an exponential growth. So this would be an example of exponential growth. If it's growing remember, it's growing by a fixed percent at regular intervals. So our equation, that would be if we have a b that's greater than 1, then we have a growth. So for example, and this doesn't match with our graph, but if you had something like y equals 15 2 to the x, sometimes you can have the b in parentheses. So this would be an example of growth because my b value, my base, is greater than 1, and it comes from the left and it grows at those regular intervals. Decay, an example of decay, exponential decay, would be if your base is in between 0 and 1. So an example would be like y equals 100 1/2 to the x. So my base is between 0 and 1. Doesn't matter what my a value is. But if my base is in between 0 and 1, I have a decay. If my base is greater than 1, I have a growth. And the graph of a decay would look like that. It's decaying or decreasing by fixed percent at regular intervals. So we can represent this pattern by the following two functions. Okay, if we have growth, then we are going to have y equals a, and remember our base. Remember from our last slide we had y equals a times b to the x. Our base has to be greater than 1, so it's actually, our formula will be 1 plus r. Okay, and my decay equation is almost exactly the same, except our base needs to be between 0 and 1, so we have 1 minus r to the x. And my y value, let's see, is the amount that we're going to have left. So the amount left over after we have a growth or a decay. So that's the y value. Our a value, the one right in front, that's going to be our initial amount, what we begin with before we have a growth or decay. Then our r value right here is going to be our rate of growth and decay. And they're usually going to give that to us in a percent, and we're going to need to make sure we put it in a decimal. And then the x, up here our little exponent, is going to represent our time intervals. So the time it's taking to grow or decay. Sometimes that can be years or hours or minutes. You have to kind of pay attention to the word problem. So this slide is very important. You have to remember our exponential growth equation, our exponential decay equation, and then what these stand for. So make sure you've written this down where you're going to be able to go back and look at it and understand. So let's do an example. We're going to have this word problem here, and we're going to use our exponential growth and decay equations to answer this question. So in 1985, we had 285 cell phone subscribers. The number of subscribers increased by 75% per year. How many cell phone subscribers were in Centerville 9 years later? So what I know is that this is going to be exponential growth, and I can tell that because of this word, because it's increasing. So it's growing. Now, that means I use my y equals a1 plus r to the x equation, my exponential growth equation. Now, this is why it's important to remember what all these y, a, r, and x stand for, is because we're going to go back into my into my word problem, and label all my variables. So it says in 1985 there were 285 cell phone subscribers. So that's my initial amount of subscribers. So remember, A is the initial amount before the growth of the decay. So I have 285, that's my initial amount. Then it tells me here that it is increasing, so that's the growing, by 75% every year. So it's growing at a rate of 75%, and we're always going to use a decimal for that. Now my x value has to do with the time intervals. Remember, this was time intervals. And they're increasing every year. And we want to know how many cell phone subscribers are 9 years later. So my time is 9 years. Now what I don't know is my y value. Remember, y is the amount after the growth or decay. That's what we want to know. How many subscribers after the 9 years of growth? So now we can go plug our values into our equation. So y we don't know. A is 285. 1 plus my rate to the power of my x value. I can simplify. 1 plus 0.75 is 1.75 to the 9. Now, because I'm not missing any variable over here, I can plug this into my calculator and find my answer. And I get that y equals 43,872. So what that means is after 9 years, I started out with 285 subscribers, but now I have 43,872 cell phone subscribers in the town of Centerville. All right, that was a lot of information, so let's try another one. This is talking about Lucy buying a new car for $28,000. If the rate of depreciation is 9%, how much is the car worth after 5 years? In this case, I'm going to have an exponential decay. And that's because of this word, depreciation. So it's a decay of the value, and that means we use y equals I didn't write that correct, 1 minus r to the power of x. So now let's go back in here and see if we can find our variables. So she bought a new car for $28,000. So that's my initial amount that the car is worth before the decay. The rate of depreciation is 9%. So my rate is 9%, which I write as a decimal. Be careful that you don't put 0.9, but 9% is 0.09. And I also have, let's see, how much is the car worth after 5 years? So that's my time interval, or my x value, which is 5 years. Y is the amount after the decay, which I don't know. So we can plug in all our values 28,000, 1 minus my rate to the power of 5. And all of this, I can simplify 1.09, 1 minus 0.09, and I have y equals 28,000.91 to the power of 5. And since I'm not missing any variables here, I can plug this straight into my calculator. And we get that y is 17,472.9. So what that means, because we're talking about dollars, she bought a car for $28,000, and 5 years later, this is how much it's worth. This is how much it has depreciated over 5 years. So I'll write that here. Value of car after 5 years. All right, so let's try a third example. The other one's been fairly easy. We've been plugging them in and putting them in our calculators. But what happens when we know Y, but we don't know AR or X? So here we're investing $2,000. How long will it take to double your investment? Because we're investing, that we know that our money is growing. So we're going to use exponential growth equation. Now let's go label our variables. So we invest $2,000 initially. So that means my A value is 2,000. It's my initial amount before the growth. My rate, it's compounded annually at 6%, which is 0.06. Now we don't know the time, right? X is my time intervals. We want to know how long it will take. That means we don't know how long it's going to take. But we know that we want it to double our investment. That means the amount after our growth, we want it to be double what we initially had, which is 4,000. So be careful when you read that. So now we can go plug all of these values in. So we have 4,000 equals 2,000, 1 plus 0.06 to the power of x. Now this is where you're going to have to be careful. We don't know our x value up here. So eventually we're going to have to change our forms. But what we're going to do first is divide by 2,000. And we end up with 2 on this side equals 1 plus 0.06. And actually I'm going to rewrite that as 1.06 to the power of x. Now this is an exponential. I'm going to move it around for me because I don't like it like that when I'm going to change its forms. But remember, when we change forms, we have b to the power of x equals a, and we change it to log ba equals x. That's an x over there. That's not helping. Log ba equals x. Okay. So that's why I rearrange from here to here. So I have the b to the power of x on the left and the argument here. You don't have to do that, but I like that before so I can change it here. So now this becomes log base of 1.06 2 equals x. And now this I can plug into my calculator to find my x value. And when I do that, I have x equals about 11.9. And because x is our time, and we know it's compounded annually, that means that it's going to take me 11.9 years in order to double my investment. All right, so let's try this last example together. This one's a little bit different. So a chemical substance has a half-life of 5 hours. How much remains? How much of a 12-gram sample remains after 12 hours? Half-life means that it is decreasing. Okay, so that should let you know that we have a decay, an exponential decay. So we're going to use y equals a1 minus r to the power of x. The other thing that a half-life should tell us or trigger for us is that it's going to change our x, what our x variable is, which we'll talk about in just a second. But my initial amount that I have before the decay is 12 grams. So I start out with 12 grams, and we want to know how much it remains after the 12 hours. So how much after our decay? We don't know that, so we're trying to find y. Our rate, if it's cutting in half every 5 hours, then it means that it's going down, right, by 50%. So our rate would be 0.5. Now let's go back to our x value, which is our time interval, right? Because it's cutting in half every 5 hours, that's one time part that we have to pay attention to. But we also want to know how much is left after 12 hours. So we've got to pay attention to both times. So anytime you see something that says half-life, so it means it's cutting in half all the time. Cutting in half every so often, or doubling, if it's doubling every few hours. That should trigger that our x value is going to be x equals the total time that we want to know, the total time of the decay or growth, over whatever the doubling or half-life time is. So in this case, we want to know how much of the sample remains after 12 hours. So normally we would just put 12 here. But because it has a half-life of 5 hours, we need to divide that by 5. So our x is actually 12 divided by 5. Total time divided by the half-life time. So if you see the word half-life or doubling in one of these problems, you need to remember that it's going to change our x value. All right, so now that we're here, that was the tricky part, but now we can do just like we did in the last 3 examples and plug into our equation. So we don't know y, we know our a, we know the rate, and we know our x. And I can simplify. This becomes 0.5. And then from here, I'm plugging this into my calculator and finding my y value. And when I do that, I end up with y being about 2.27. And remember, we wanted to know how much of that 12-gram sample is left. So after 12 hours, I have 2.27 grams of my chemical substance left. So if you want to write out some steps, if that's going to help you, the first thing we always did in those word problems was identify if it's exponential growth or decay. That way we can use the correct equation, either the 1 plus r or the 1 minus r. Then we identified our variables, right? We want to know if it was y, what our y was, a, r, or x. We're always missing one, so then when we're done with that, we solve for the unknown. Now this part is a little bit tricky, right? Solving for the unknown could involve just plugging everything into the calculator. We might have to change forms. So just be careful when you're solving that you're solving correctly with the things that we've learned in this unit. And the last thing I don't want you to forget is anytime you see the words half-life or doubling time, that should tell you that your x value is going to be total time over whatever your half-life time or your doubling time is. Now I know that was a lot, so please go rewatch as necessary, and this video will be up, so you can go back and rewatch it as many times as you need to before the test, and we are going to practice exponential and decay for 3 days, also in class. All right, thanks for watching. Goodbye.